Hey everybody, and welcome back to Computers and Computations. This week we're going to be talking about the difference between digital and analog computation and why this distinction might be important. So hope you enjoy the talk. Okay, so without further ado, let's get into it. Okay, so throughout this course we've been looking at different models of computation. For instance, we've looked at deterministic Turing machines, non-deterministic Turing machines, quantum computation, among a few others. And what we're going to look at today is a distinction that pops up in the philosophical literature, as well as some of the computer science literature, on how to distinguish between digital and analog computation. So what is a characterization of the difference between digital and analog, and how does this play into characterizations of different models and examples of computations? So here's what we're going to do today. So firstly, I'm just going to go through some rough examples of the difference between analog and digital computation and talk about what the rough idea seems to be concerning the distinction. Then next we'll look at some characterizations that have been proposed in the philosophical literature. And I'm also going to then, in section 3, talk a bit about what the upshots of the efforts to make this distinction have been, raise some questions, and leave things pretty open. Good. So a central concept throughout the course has been the Turing machine, and this is in some sense going to be the kind of canonical model of a digital computer. So how does this work? Let's remember, you're probably familiar by now, but it doesn't hurt just to go over it. This is a tape. There are cells. They have zeros and ones in them. There's a read head and a write head, and it can change what's in the cell. So it might, for instance, get rid of this 0 here and change it into a 1 and then move left or right. Okay, so this is the idea of digital computation. There are digits being modified, right? We might have a larger alphabet, might not just be zeros and ones, but in each case, there's digits being modified, and they're being modified in a very discrete way. I can't, for instance, if I go over to this cell, I can't draw half a 1 or something like that. It's either a 1 or it's a 0. There's no other options. So this is the idea of digital computation, and the Turing machine is the sort of very robust, idealized example of a digital computer. It's an interesting question exactly where modern, actually existing digital computers fit on this kind of scale, because obviously there's kind of imperfections in how they actually operate. But just for the purpose of getting a handle on the idea, I think the Turing machine is the easiest model to work with to begin with. Okay, so what's the idea of an analog computer or computation then? Well, if we're thinking of a computation as roughly some sort of mechanical way for solving particular mathematical problems, right? Digital manipulation is not the only option, so changing digits is not the only way to do that. A nice example here is the use of a slide rule. So you can look up various videos of slide rules working on YouTube. So I'll just describe the rough abstract idea here. In a slide rule, you have various lengths on a logarithmic scale, right? As you can see there. And what we're going to do is, by manipulating various lengths and sliding numbers backwards and forwards, you can match up the different logarithmic scales up, and this will correspond to various kinds of operation, right? So it's a simple example of multiplication. what you're doing by lining up different parts on the slide rule is you're effectively converting the numbers you want to multiply to logarithmic values, right? And then you can use the fact, to do with the mathematics of logarithms, for instance, that the log of the product is the same as the sum of the logs, right? To manipulate these lengths and calculate things like products, and this can be generalized to various other kinds of operation as well. And then at the end, you can read off on the slide rule the result that you want to get by taking the antilog, right? So in this case, for instance, with products, we transform the first number, or the numbers we want to multiply, into their logs, right, by putting them in the appropriate places on the slide rule. And you add the lengths, right? That's when you're gonna move the slide rule. And because you know that adding the lengths will give you the log of the products, you can then read off on the slide rule what the product is, for instance. So in this context, we're not really manipulating an alphabet or digits in any sense. You're using the fact that there are resemblances, it seems, between the structure you want to compute over and something in the physical world, right? Perhaps with some encoding on it to calculate the relevant operation you want to do. And in particular, it's not just that there's this analogy going on in the case of a slide rule, for instance, but also that the particular things you're modifying, in this case, like adding lengths, these are not discrete things, right? In the slide rule, you can, with a bit of idealization, move any continuous amount, right? It's not like I have to only move a discrete amount, or delete a 0 or delete and add a 1, for instance. Okay, and we'll see that this comes out in the different characterizations of what the difference between analog is later. So the difference between modifying discrete magnitudes is one way we might go, and versus continuous magnitudes. And the other way we might go is drawing very heavily on this idea of an analogy between the thing being manipulated in the computation and the structure you're trying to compute for. Good. So that was the slide rule. Let's just mention some further examples we might want to have in the backs of our minds here. So one idea is the use of solar systems, or models of solar systems. So if I have some sort of steampunk style model of the solar system here with various other planets orbiting, and maybe I crank some sort of handle, for instance, and the celestial bodies will revolve according to the handle. I can use this, for instance, to compute the relative positions of planets. So I crank the handle a number of times corresponding to, let's say, a year, and after that year, I will then be able to calculate, for instance, the distance between these two celestial bodies on the basis that it's a good model, and so forth. Yeah. So this is one kind of example we might have of the use of analog computations. And this shows also that the idea of analog computation goes way, way, way back in human history. I mean, people have been building these sorts of models and trying to figure things out for a very, very long time. More recently, there was a period in which digital computers were comparatively slow, and you could get a much better reading quickly if you rather than modeling a particular phenomenon digitally just by using an analog kind of model of the phenomenon. So an example here is the use of electrical components like resistors and capacitors in modeling mechanical phenomena, right? So springs and masses, etc. Fluid dampeners, things like this. So the similarity between the equations governing them can be leveraged to get, for instance, a computation of how a spring and a mass will behave using a capacitor. And this is very advantageous because, if I want to actually check how the spring and mass, some spring with a particular mass behaves, I have to actually, change out the spring, change out the mass if I want to measure different springs and masses. Whereas for a capacitor or with a resistor, for instance, I can just vary various electrical parameters, and that might be far, far cheaper than and more time efficient than changing out the springs and the particular masses and how they're behaving. So in this context, for a while, analog computers were also far quicker than digital computers because I have this kind of direct resemblance in certain cases between the structure I'm trying to compute and the computational parameters, as it were. If I want to do this digitally, for instance, I'm going to have to figure out some way of encoding the springs and the masses, right, into a digital format that's then available to be manipulated, whereas many of the analog computations just work directly. Okay, so this is the rough idea between digital and analog, and there's a question now, right? As philosophers, how should we understand this difference? How can we come with a characterization of this difference? And I think tangentially linked, how important is this difference once we have it? Does it matter for how we view different kinds of computation and how we look to develop computations? Or is it just a matter of mere intellectual interest that you can come up with different particular taxonomies? Good. So before we get into exactly specific proposals for how to characterize the distinction, we should note that there's prior questions that perhaps should be addressed, right? So for instance, what are the objects to which digital and analog computation applies? What are the bearers of the term digital or analog? And there's various kinds of things we could pick here. So one, it could be the machines themselves, right, independent of any particular process, just the nuts and bolts, so to speak, of the actual objects performing these processes. Secondly, it could be the processes that we think are digital or analog as opposed to the machines themselves. This includes the input and how things are manipulated and the output. And finally, it could be something more subtle. It could not just be the machines or the processes, but it could be some relationship between machines and or processes. So it might be that different things are going to count as analog or digital depending on how they're being interpreted. And this is really important, I think. This is something that we'll return to a bit later, and I think it's one of the very interesting things that comes out of this debate. Right, so with this in hand, let's look at two kind of options for bearers of the computation. So one option is that we say it's the machine that is bearing the computation, and the other one is the representation of the input or output that we pick, right? So within these two options, there have been two core ways of interpreting the distinction between digital and analog. And they roughly, you get a rough kind of mirroring within the two options. So the first option within option one is that analog computers have continuous internal states and digital computers have discrete internal states, right? So when we have a Turing machine, right, we can never draw half or one or some value in between 0, 0 and 1, right? It's just either we get 0 or we get 1, given that that's the alphabet, of course. On the other hand, in analog computation, like we have some slide rule here, right? And I can move this middle bit of the slide rule. I can move it, presumably, perhaps with a little bit of idealization, any particular real number I want. So I could move it potentially, pi centimeters, for instance, right? Whereas this is not possible with a standard Turing machine that has finite alphabet. So that's one characterization. It's on the internal states of how the machine behaves, and the distinction is between the continuous and the discrete. And the second option is what we discussed a little bit earlier, that analog computers depend on an analogy between the states variables of the machine and the target problem, whereas that's not present in the digital case. So this position argues. So for instance, where we have a model of the celestial bodies, right? And this is our computing device. What we're trading on here is that this model of the celestial bodies that we're going to use to compute bears an analogous relationship to the actual celestial bodies that we want to find the positions of, right? So, if the distance here is 10 centimeters, let's say, that presumably then corresponds to, given the scale of the model, some actual distance between, let's say that's the Earth, and then that's Mercury or whatever, right? So this is the difference. On the one hand, we have continuous internal states, and on the other, we're trading on some sort of analogy. Okay, this is exactly mirrored within option 2, where we talk about the representation of the input-output rather than the internal development of the machine. So we've got exactly the same options. One is that the input-output are continuous variables rather than discrete. And the other option is that the input and output are somehow analogous to the relevant phenomena of the structure that we're trying to compute. Good. So there are at least a couple of problems that have been identified with the analogical account of analog computation, that is the kind that requires us to be talking about analogies with respect to analog computation. And this can be put as a problem of both necessity and sufficiency. So it's neither necessary nor sufficient that a computation has some sort of analogy going on for it to be classed as an analog computation. So on the necessity side, it looks like there are analog computations that don't bear any relationship or any analogy to the relevant phenomena. So one example here might be an analog clock that we're all familiar with. The hands move, and this lets me tell the time of day. So you might think that this, given a particular day, particular season, etc., if I wanted to, I could add in a date counter there if really necessary. We could view this as a way of computing, for instance, the position of the sun, or whether it will be light or dark. This looks very clearly like it's an analog computation, but it's very unclear what the analogy might be between the clock face, as it were, and like the position of the sun in the relation to the Earth. But that seems like a perfectly legitimate computation. Now, maybe there are responses here, but it does seem, at least that in this case, that any analogy between this legitimate kind of analog computation looks like it might be a bit tenuous. So that's the first problem. It's a necessity problem. It is not necessary for a computation to be analog for there to be a relationship between the computing device and the target phenomena. Okay, the second problem, nor does it seem to be sufficient that there's an analogy between the target phenomena and the relevant kind of computation for it to be an analog computation. So here's one thing we might want to do in a particular kind of very specific circumstance. I get given 2 rows of sticks, right? This is what these are representing here. These are 2 rows of sticks. And I want to know how many sticks are going to be in the row if I put them together. Right, so in this case, it's going to be 7. And I can very accurately model this situation with a particular Turing machine, right? In fact, we can use the old algorithm that we talked about for computing the length of 2 blocks of strokes, where we go to the end, we rub out that one, replace it with a 0, then we go back, we find the 0 in the middle, we put a 1 there, and then we go back and we halt on the leftmost stroke. Similarly, we could do a very similar operation on the sticks, right? We just go and we pick up this stick and we put it in the middle, and then we look at the number of sticks we get in the row. Now, in this case, there's a very, very tight analogy between the target phenomena, namely the sticks, and the what's going on the tape of the Turing machine, right? But it's not the case that that is an analog computation. That seems very clearly to be a digital computation. Okay, so this is a case where we have an analogy between the computing device and the target phenomena, but we want to say it's digital. So it's not sufficient for there to be an analogy for it to be an analog computation. Okay, so I think this is very problematic for the analogy view as a general theory of what it is to be an analog computation. But I do think the analogy view raises something really, really important. Namely, there are these class of computations, both digital and analog, right, that we might call analogy-based, right? That they're depending on a direct analogy between the target phenomena and the states and or input and output. And I think one interesting question here is, to what extent are these kind of analogy-based computations really just instances of physical modeling? For instance, we can think of a design for a plane, and we make a miniature version of this plane, right? It's my wonderful drawing of a plane, and we stick it in a wind tunnel, and we look at how the wind behaves with respect to that plane, and that might influence our plane design. So we can ask here, what is the relationship between these more kind of computational processes and physical modeling? Are these an instance of physical modeling? And is, in a way, physical modeling, say with scale models, is this a kind of computation in a way? I think this is an interesting question, at least for informing some questions in the philosophy of science about how we think computation and physical modeling can be related to one another. Great. So given these problems with the analogical account of computation, it seems that a more promising route is to look at analog computations as involving continuous magnitudes rather than necessarily involving analogies. And I mean, there may be other accounts of analog computation, but let's go with the continuous account for now. If we do so, there appeared to be some difficult but interesting questions here. In particular, there appear to be hybrid cases, or at least cases where it's unclear whether a particular process or machine, let's say, counts as an analog or digital computer. Okay, so here's an example of this. I have, let's suppose, a cylinder that I can add gases to. And let's just consider the following completely physical description of what I do, independent of any computational ideas. So firstly, I fill the cylinder up with 2.1 atmospheres of some gas, and then I add in another 3.1 atmospheres of gas afterwards, and there's a dial I can read off on the cylinder, which obviously reads 5.2 atmospheres after I've done that. Now, I could view this as a particular kind of computation, and there are two different ways I could view this in virtue of the fact that we're thinking of things as continuous magnitudes. I could view it as an analog computation of the fact that 2.1 plus 3.1 is 5.2, right? Presumably, I could have added in instead here 3.11 atmospheres. This would have read 5.21, let's say. Let's suppose I have precise enough dials and so forth. And then this would be a computation of the fact that 2.1 plus 3.11 is 5.21, right? Alternatively, I could read this in a much more digital fashion, right? Let's suppose up to some tolerance, I regard this as an input of 2, right? Let's suppose I have to remain within 0.1 of a value in terms of atmospheres in order to count as that value. We'll get rid of this one here, and then this is an input of 3, and then we read off the output as 5. This could be a computation of 2 plus 3 equals 5, but reading these as discrete inputs rather than continuous inputs. So there's a sense in which just the mere physical description of this process, independent of any description of what we are meant to be modeling or representing, what problem that is designed to compute, is just it's unclear which computation it represents. And we could do a very similar thing if we had just like a regular digital computer, for instance, right? A regular digital computer is doing some computations on some relevant code, but there's also a bunch of like resistors and so forth in that. And we could view, by just attaching, let's say we have a device attached to a particular resistor, and this is modeling, let's say, the behavior of a spring or something like that. We have just the mere physical process, the mere machine itself, we could view as both executing a particular computation via, manipulations on the machine code, or we could view it as a computation given the behavior of this particular resistor, for instance. So these can be translated into different contexts. It's unclear just via the description of a physical object whether that thing should count as an analog computation or a digital computation in given different descriptions. So it seems, given this, that whether or not a machine or process counts as an analog or digital computation or computer depends partly on how we are interpreting the computation, and that goes within the different kinds as well, right? Exactly what we are taking the relevant process to encode either an analog or a digital computation can affect what we take the problem being solved to be, right? After all, at root, all these computers, either analog or digital, are just some sort of physical process, or perhaps idealized physical process, right? Like a Turing machine. It's very idealized, but nonetheless, it's meant to be representing some sort of idealized idea of a process. And once we have this idea that exactly what we're computing depends on how we or some agent relates to a physical process, we get immediately some very difficult questions, but also some very, very interesting questions. So here's some particular upshots and questions we might raise about this situation, and I'll just present them and then leave it for you folks to think about. So firstly, what about if or when AI takes over some programming roles, okay? So it's becoming more and more common that we develop artificial intelligence for doing things that are normally done by people, and perhaps at some point writing serious software will become part of that, okay? Now, once that happens, there's a sense, or there's at least a very deep question about who the agent interpreting any code produced by such an AI would be, right? Remember, here we're looking at a physical process as computation, just in case it's designed to fulfill a very particular purpose, and this requires some interpretation on the part of the person who has put it to that task, right? Or the agent that has put it to that task, perhaps it's better to say, right? So who is the agent doing the interpretation there? Is it the AI, right? And in that case, does that change our view of any questions in artificial intelligence? Or perhaps it's the person who programmed the AI that then went on to design code for particular purposes. But there's at least a possibility that in this case, where you're ascribing the interpreting agent to be the person who programmed the AI, that there might be purposes, in inverted commas, that this agent here, the person, can't understand, right? It might be that the AI is just designing very, very complicated code that fulfills purposes that the person can't even comprehend what those purposes are, right? And if that's the case, then it's really weird to assert that this person here is the interpreter when they potentially can't even understand what's going on. So that's a very interesting case, and I think it bears some more thinking about exactly what we are expecting out of interpreters in the context of these computations. There's also an interesting case about when there are programs that are now not solving a particular single problem or computing a single problem, but rather undergoing designs to be computing in an informal sense very different, just like a continuous phenomenon. So one example here is GPS monitoring, for instance, right? There is no single computational problem being addressed by a GPS computing algorithm. It's rather that the GPS is computing many different solutions, right? With the target then being to model in the end your position. But there's not like one single computational problem that is solved and then it's computed in the case of GPS monitoring, right? So there's a question there of exactly what we think that algorithm is doing and how to interpret it. I think there are responses here. For instance, one response that is very natural is that actually this purpose of GPS monitoring seems to be subdividable into a cluster of different separate computational problems that fit together to give you a modeling of the phenomenon of GPS monitoring. Another question we might ask is whether a process can ever stop being a computation at some point, say because we lose interpretive control over it. So for instance, in the AI case, you might think that at some point, once we've, this AI has really run away and started programming stuff that we can't even interpret, if you think also that AIs aren't agents in any sense, that's a very controversial assumption, but let's suppose you think that, then perhaps you think because of the lack of an interpreter, an agent interpreting this process, this now becomes a mere physical process rather than a computation. Okay. Another example might be that we have computers running, right? And then all possible agents suddenly die, right? The computers that we have left over, right? Suppose that they initiate some task that we didn't envisage. Are those then performing computations, or are they just merely atoms bouncing around in certain ways? These are very interesting questions, and this relates to how information and computing are integrated and exactly the role that agents have within that relationship between processes and the encoding of information. Okay, one final question I want to raise is what exactly we think about quantum computation. So recall that for quantum computation, we have some particular quantum states, and we input them into some quantum circuitry. At the end, we make a measurement and we get the output either 0 or 1 after making that measurement within some probabilistic tolerance. Okay, so here, assuming the standard mathematical modeling of quantum mechanics, the input and the manipulations are mostly continuous, right? We're modifying the relevant positions of different qubits, right? However, the final output is always digital. When we finally go to make a measurement, we force all the qubits into or the relevant qubits into either a 0 or 1 position in order to read off the answer. So there's a question here of, does this count as a digital computation? Is it an analog computation? Or is it maybe something else entirely? Maybe quantum computing deserves its own kind of taxonomy. The interesting thing here is that you have very continuous things happening here, but then the eventual output is always a binary output, right? Depending on where you go with this and where you fall, so if you do think this is a kind of analog computation or perhaps some sort of hybrid, it might be that you think that analog computations, especially if you remember that we talked a bit about BQP, right? If it turns out that BQP is a strictly larger class than P, this is not known, but if we assume that that's the case, then you would have a situation in which you have serious speed advantages to be gained by considering analog or hybrid systems. And this is very interesting because it sort of looks like there's a circle here. It used to be that analog computations were a nice way of giving you a much faster result than digital computations. Gradually, digital computations, certainly in the last 50 years or so, have become very, very efficient and been used to model lots of analog phenomena instead of analog computers. Whereas perhaps you maybe think that quantum computation, if you think it's a kind of analog computation, is a possible resurgence of this speed advantage of analog computation over digital computation. Okay, grand. So that's a bunch of questions about how we define analog versus digital computation. I just want to sum up with a couple of points that are the main takeaways, I think. So first, once you've settled on a particular definition, there's then another question that has to be asked of what counts as a particular analog or digital computation. We saw that on the last slide with quantum computation. It's not entirely clear. Perhaps the more interesting question, rather than just coming up with a good taxonomy between analog and digital, is why we want to have this distinction. What's important about the distinction between analog and digital computation, right? And I think two things that come out of this debate, especially interesting. Firstly, is that it really indicates, especially these systems where it's unclear whether they should be analog or digital, that part of what's going on in any computational procedure is has a relationship between an agent and the agent doing the computation. There's just too many physical processes, in a sense, for them all to be counted as computations without thinking about how the information is being encoded into the physical processes, right? And that's something that looks like it needs an agent of some sort to do, right? And the second question is, look, perhaps we can leverage this distinction by thinking about how analog and digital interact with one another. So you might think this is part of what's going on in quantum computation. We're leveraging an analog relationship or an analog behavior of the qubits, and when we're leveraging algebraic relationships between how those qubits behave and problems in order to get a digital answer within some probabilistic tolerance. You know, maybe there are other kinds of hybrids, not just quantum computation, that give us new technologies, perhaps different speed advantages. And I think that's a really interesting question to ask, that how, as philosophers, should we view these engineering activities, and is there anything that we can contribute to an understanding of how computation works in general? Okay, great. So that's the last video in this lecture series on computers and computations. If you've been following along, I do hope you enjoyed it. I'm always enjoy talking to people. So if anybody wants to, you can go to my website and there's a contact form there through which you can reach out to me. Yeah, thanks for listening. And I hope you enjoy your studies further looking at computers and computations. I'm certainly looking forward to seeing how my own thinking on the topic develops over the next few years. All right, bye-bye.